Hello. Hello, Katya. Hello, Sarah. Hello. Wait, yes. Hello, Katya. Hello, Sarah. Hello, Euban. Hello, Jose. Hello, Kay. Hello, Ashley. Hello, Tobias. Hello, Abdel. Hello. And now you're being okay. You're hello. All right. Now that's what I'm talking about. You're supposed to beat me, guys. It's like a competition. Well, it's like a competition, except everybody's a winner. So hi, Kay. Now I'm going to the chat. That was like the video. So hi, Kay. Good afternoon, Jocelyn. Hello, Brian. Good afternoon, Jose. Hello, Euban. Hello, Gianna. Hello, Alejandro. Hello, oh, I just lost Scroll City, USA. Hello, Ashley. Good afternoon, Stephen. Top of the afternoon, Abdel. Hello, Tobias. Where's the Pokemon, Tobias? Wait, where's it? Oh, I see. Oh, I can't even see what that is. That is definitely a new exotic. Okay, that's awesome. Good afternoon, Katya. Hi, Jasmine. Awesome, awesome. And remember, you're all allowed to beat me to that. You know, I'm just saying. But okay. Oh, wait. So I said, wait, Tobias, Ashley. Oh, hello, Gianna. I think that's it. Did I say Jasmine? Did I say I did? Yes, Abdel, Kay, Jose, Katya, Steve. I know it all seems like this is all just like secret attendance taking, but it totally isn't. Why this is not attendance taking is because I'm only aware of people who are here. If you're not here, I don't know who you are, and I'm not writing that down, just to be clear. Okay, it's really all about humanity. Okay, cool. Again, wait, are we? Yes. So stop me if there's any questions. I think we are really starting to make progress in this class. Oh, hello. Wait, excuse me. That's a disaster. 1 second. Okay. Boom. All right, there we go. Boom. So we're going to continue today. We're in the middle of going over homework 4. Yes, we're in the middle of going over homework 4. We're going to continue that today. We're in the middle of practicing or like introducing ourselves to the equation that is at the top of this sheet right here. I mean, the first equation, we introduced that last class. We also, in the context of introducing that, we also introduced a different equation, which is not the one that's written on the bottom of the sheet. Like, so we introduced the top equation here, which is the definition of average acceleration. It says that average acceleration is defined to be change in instantaneous velocity per time. So it's starting to get into a bit of a mouthful there. And we're practicing the whole context. I mean, the whole thing of homework 4 is like sort of seeing that equation in action or beginning to practicing, etc. But just to try to be clear, like, that equation is saying that average acceleration is defined to be change in instantaneous velocity per time. So therefore, last class, we had to take a little bit of a side road and provide a definition equation for instantaneous velocity itself. That's a separate equation that we got last time. In other words, as of right now, as of this moment, I think we have 4 equations so far in this class. Sorry, 3 equations so far in this class. We had 3, one for average velocity, one for average acceleration, which is the top one right here, one for instantaneous velocity. Then we're going to get a new one today. By the end of this class, there's a new equation written, like the second one written on this page. We're going to get that by the end of today. Hello. Hi. Hello. We're going to get, bye. Love you. We're going to get that second equation by the end of today. So just to be clear, that will mean we have a total of 4 so far in this class, just 4, but they're starting to get a little bit thicker. I also just want to say quick. So, you know, it's always kind of like I'm trying to do like the equation where we're at and the equation where we're going or something on the board. But one thing I just want to highlight, since material is starting to accumulate here, maybe, if you back up and consider it, we now have 3 related but distinct threads going in this class. We have like 3 ways that we're talking about velocity all at the same time. And in fact, that actually is a 4th. Yeah, I guess we really have 4 equations already so far, but we we have three threads going about velocity all at the same time so far. We have a concept of average velocity. That was the very first equation of the year, of the semester. We have a concept of instantaneous velocity. That's the equation from last class. So that's two different things. One is v with a bar over it. One is v without a bar over it. So you have average velocity and instantaneous velocity. Then we also have this larger conceptual, principled idea that all velocity, whatever kind of velocity we're talking about, whether it's average or it's instantaneous, any kind of velocity we're talking about is actually a relation between two objects, not a property of one object, right? And that's the whole discussion from homework 3 and train of thought and planet Earth and all of that, Galileo's principle and all of that. So that's three things we're saying at the same time about velocity. There's average, there's instant, but either one you're talking about, no matter what, velocity is a relation between two objects. It's dependent on the frame of reference, the perspective, the coordinate system that you choose, more than it's dependent on whatever object that you're talking about. And even that third thing that I just said even leads to equations, one of which we called GPR form number 4, and we wrote down a couple of days ago. So there's three separate things that we're saying about velocity, always, kind of three tracks that are always running, and they're all intertwined, they're all related, but it shows you, it's kind of meant to show you how thick and deep the notion of velocity really does go in physics. We're going to keep talking about velocity in a way forever in physics, because velocity is the simple ratio, is a simple expression of a motion through space per time. And that's what all of physics is about, motion through space and time. Okay, so I don't want you to confuse the equations or think that they're redundant or contradictory or meant to be confusing or anything like that. There's a lot of things that we're saying about velocity as we track the material. Finally, you see, if you're looking at the screen right now, there's going to be yet another equation that's going to come today, by the end of today. Another equation that is new, the second one there. We're going to explain it and develop it today. It's yet another equation about average velocity, or about velocity. It happens to be another one about average velocity. If you're tracking this, you already have an equation for average velocity, but this is a new, different one. It's neither redundant nor is it contradictory to the old one. You sort of have to pay attention, so that's like a teaser for the end of class today, or a foreshadow or whatever. A teaser, no, what's a teaser? What do you call that? What do you call that when you give away the end of the movie by accident? That people hate when people do that. Well, anyway, by the end of class today, like we're gonna have another equation, the left side of which is v with a bar over it. But it's new. It's not any of the ones we've gotten before. It's related but different. So we have to keep track of all this. Okay, but that said, so anyway, where we are is the first equation. Where we're going to get to is the second equation. That will really be the sixth total equation that we've gotten so far in this class. And when we're done, probably next class, I'll start with just a list of all the equations so you could see it like plainly in my notes and your note. But if you're tracking this, yeah, I think by the end of today, we have a total of 6 equations that you really want to know inside and out and be able to use. Okay, but there's all the context of homework 4, which we're going back to now. Again, also just another quick note, like the homeworks are coming back. They are in a scattershot kind of weird way. Some people have gotten a lot back. Some have gotten, it's just the way the notifications are coming into my device. I apologize, but they'll keep coming. You don't have any new homework due until Friday of this week. But we're almost caught up to that homework in terms of going over things. We will be. And by the end of today's class, we'll be done with going over homework 4. So what's due will be homework 5 that's due this Friday. But just again, because there's still a bunch of things that are coming back to a bunch of you, like more people are owed, some people are owed a lot from me, some people are owed less. But no matter what, please take that as a sign that anything that you still might owe me, I will gladly still take. And there are not, we're still, this is like the IRS during COVID, like there's a no penalty zone still. Do not give me something because you think it's too late to be worth it or something, or because you're embarrassed or like I will take anything still and you'll get credit for it. And people that have been handing in things earlier, lots of revisions, that is equally very much noticed, believe me, and better for them in the long run, believe me. But no one's being penalized or punished for anything late or anything like that. So wherever you are, if you've never done homework 1, like do it, you know, if you, etc. Okay. Okay, so I'm going back to homework 4. We're in the middle of homework 4. We're on question, I think it is 3. You'll see in a second. Hopefully you're looking at the sheet as you follow, as the original sheet as you follow along, because I can't share the sheet and this board. But so we're going to homework 4. Okay, here we go, homework 4, and I'm changing the view. So homework 4, we're going to problem Roman numeral number 3. Oops, sorry. The problem itself is entitled average acceleration, as in getting used to the definition of it. Okay, so here we go. All right, so it gives you the definition in the sheet. It writes it a slightly different way. We should be increasingly flexible about that too. Different sheets or different textbooks or different websites use slightly different symbols. The more, and this is also partly why I always try to introduce all this first conceptually or in English, and then we're trying to notate things with symbols. But you know, you don't want to be so tied to the symbols that you can't be flexible about them. So in the sheet, it says like delta V over delta T. It says it that way because it's trying to reinforce. This is another kind of like slope thing. This is another thing if you were to make a graph of V on the y-axis and a graph of T on the x-axis, right? Then average acceleration kind of equals the slope of a straight dotted line connecting any 2 points on a VT graph, right? It's the change in velocity per the change in time. But the way I write it is generally in class is the way it's written right here. Excuse me, on this board, V minus V naught over T. Change in instantaneous velocity per time. All right, so in this example, we're given a 1975 Toyota, and we're given some facts about it, that the Toyota goes from an initial velocity of 0 miles per hour to a final velocity of 60 miles per hour. So if I'm doing the homework right now, right, first I've drawn a little diagram. It's not a work of art, but the point is to get labels in that diagram that make clear all the facts that I'm going to use in the problem. The diagram doesn't solve the problem. The diagram presents the problem, right? Okay, so it goes from 0 miles an hour to 60 miles an hour in 2 minutes. And the question A, let me just fix my pen. So the question A is, in miles per hour per minute, what is the average acceleration? In fact, let me even, miles per hour per minute. Now, you might think that's a funny way of talking about acceleration. That's part of why I'm assigning this problem. It's one of many ways to talk about acceleration. I think it may not be the strictly classical metric system way, but I think it's a very expressive way. We'll get to that. But no matter what, we're asking for acceleration. So we use the definition, we're asking for the average acceleration from 0 to, for this situation, for a car that's gone from 0 to 60 in 2 minutes. So I'm going to use the definition of average acceleration, A bar, triple equal sign, V minus V naught over T. Now, and I'm going to solve in a second. So I've done step 1, DFP. Please, always, if you lose any points in homework or an exam, and I write DFP, it means I need a diagram, please, before you're doing anything. So I did a diagram, then I wrote what the question is, WIQ. Step 2, I wrote A bar equals what? Okay, so then I wrote A bar. So now I'm done step 3, GDP, A bar, triple equal sign, V minus V naught over T. Please notice too, I believe here, I am giving you every one of the steps. I'm doing every step. I'm not labeling them step 1, step 2, step 3. You certainly can, and that's great, and I think it's helpful. Sometimes I do. I'm not labeling them here, but I'm still definitely doing every step and making them separate. So I'm up to step 3, GDP, like the definition of acceleration average is that. Okay, so next page. So now I'm doing PAW step 4. I'm working it out, plugging in the numbers. Someone's here. Okay, so I'm plugging in the numbers, 60 for the final instantaneous velocity, 0 for the initial instantaneous velocity. And I'm dividing by the total time of 2 minutes. Quick, and then I'm doing the math, right? And I have a final answer circle. So that's all PAW step 4. Now I do the math, and then I have a final answer circled. That's step 5, FAC. That's my last step. And my final answer for average acceleration in the units that I'm being asked for here, my final answer is 30 miles per hour per minute. Or you, in other words, 30 miles per hour per minute, or in other words, 30 miles per hour per minute. You can write it any one of these ways, right? I want all these are equivalent. Miles per hour per minute, or miles per hour per minute, or miles per hour per minute. There's a number of important things to notice here. This is obviously just meant to be an exercise. It's not meant to be a trick. It's meant to be straightforward, but I want to point out some things about what acceleration means here. Okay, first of all, it's average acceleration. Just like we had a concept of average velocity from one point in time to another, this is average acceleration from one point in time to another. It's average in the sense that all I know is at the beginning of 2 minutes, this car was at rest. And at the end of 2 minutes, this car was traveling at an instantaneous velocity of 60 miles per hour. So I know it took 2 minutes for it to accelerate up, to change its velocity up from 0 to 60. So I divide and I get that on average, it's gaining 30 miles per hour of velocity every minute on average. Why am I saying on average? Because what this means is, according to this pattern, it's like a pattern. It's one number to describe something that's changing all the time. According to this pattern, another minute later, it'd be going 90 miles an hour. Excuse me. It'd be going 90 miles an hour. Another minute after that, it'd be going 120 miles per hour. Another minute after that, it'd be going 150 miles an hour. Like if it kept up this trend, every minute it's gaining on average 30. But I just want to be clear, it's an average because I don't know for a fact that what it did from 0 to 60 or what it did for those 2 minutes was that constant or steady. It might have sped up in a drastic way at the beginning and then tapered off and then sped up again. Like, I don't know if someone was shifting gears while they were driving this car, or even if the car lurched in reverse and then compensated. Like, I don't actually know. If I made a velocity time graph, I know one point, I know the other point. So I know that if I drew a dotted straight line between those 2 points, the slope of it would be 30, but I don't know that the car actually accelerated in this steady way. I don't know if that makes any sense or not, but this is an average. It's telling me on average for those 2 minutes, the rate at which it accelerated. Now, furthermore, the units are kind of the focus here. Notice that the units, however you write, you might think the units are kind of funny. They are kind of funny, but they're not wrong. No matter how you write them, wherever you put that, your slashes and your fraction signs, the thing to understand is that one way or another, I have a unit of space, of distance, of displacement, whatever, in the numerator of a fraction. And then I have two distinct units of time. I have two distinct references to time in the denominator of this fraction. No matter how you write it, they are each in the denominator ultimately, which is why perhaps the most elegant or tightest way to write it is to say miles per hours minutes. Like I'm trying to say explicitly that hours and minutes are each in the denominator. Now, why are there two different references to time? Because we're talking about an acceleration here. We're talking about a change per time of velocity, which is distance per time or displacement per time. Like there's definitely two references to time here. In other words, this thing is not saying that we're traveling at a velocity rate of 30 miles per hour or a velocity rate of 30 miles per minute. That is not what this is saying. We're not saying that every minute the car travels 30 miles, nor are we saying that at every hour the car travels 30 miles. I don't know how far the car has traveled. Like, let me be very explicit about that. We're going to need another equation or another new set of thoughts or another problem later on down the line to actually figure out how far this car has traveled in the 2 minutes. I do not think, or in 1 minute or whatever, I do not think this car has traveled 30 miles in a minute. And I do not think this car has traveled 60 miles in 2 minutes. Like, think about that for a second if that bothers you, or tell me if that bothers you. All I know is that in 2 minutes, it raised its velocity from 0 miles per hour to 60 miles per hour. In other words, this is not the rate at which the car is traveling. This is the rate at which the speedometer needle is traveling across the numbers, right? This is not the rate at which the car traverses spots on the ground. This is the rate at which the speedometer needle traverses markings on the speedometer display, if that makes sense. This is how quickly we're moving through speeds, not how quickly we're moving through space. So speed is distance per time. This is distance per time, and velocity is displacement per time. This is displacement per time. This is saying every next minute, we're changing our velocity by 30 miles per hour. So that's why there's two references to time. Now, I'm almost moving on. I'm sure some of you are like, yeah. And I apologize. But that's why there's not only two references to time, but that's why the two types of time in this case, given the numbers that we were given, are two different types, hours and minutes. Because a lot of us can relate to miles per hour as a speed, and a lot of us can relate to minutes as a time interval. So it's saying, look, every minute, this thing is going faster by 30 miles per hour. Yo, like that's what it's saying, right? In 4 minutes, I don't know how far this thing has gone, but I know in 4 minutes, it will be going 120 miles per hour. So it's 30 miles per hour per every minute. That's what we're saying. Two references to time. Okay, so that's the answer to that one. Definitely stop me in the chat or anywhere else if you don't like that, but that's the answer to that. And I think it makes sense. 30 miles per hour per minute. That's on average the rate at which this thing is changing velocity. But now you might say, okay, but that's clunky. Like I get it. Yeah, remember, it doesn't seem very scientific to me, or it doesn't seem very proper, like hour per minute. Can't we like clean this up a little bit? Sure. We can clean this up. First of all, yes, sure. We could talk about meters instead of miles. And from here on, and usually we'll talk about meters instead of miles. Yes, the metric system is better. But right now, since we all relate, well, since many of us relate better to miles, I'm leaving it as miles. And that's fine. It's just not the metric system. But you might say, yeah. Fine, miles. Yeah, remember, you can have your miles. But what I don't like is this hour minute crap. Like, can't you do something to make that, so that the units are the same? Sure. So the next question asks, instead of miles per hour per minute, the next question asks for miles per second again. Like it asks us to convert to seconds. It could have asked us to convert to minutes or hours. It could have done anything. But the key thing is that the next question is asking us to get both of our time references to be in the same units. So it's going to be, we're going to try to convert this to make it miles per second again. Or in other words, both seconds in the denominator. So seconds times seconds. And we're then just going to shorthand that. We're going to abbreviate seconds times seconds as seconds squared. We're going to try to convert this because question B asks us to. We're going to try to convert this to 30 miles per second squared. That's what we're going to do. I'm going to turn the page, obviously, but I also just want to warn you. And yes, many of you may remember from high school that that's more traditional to talk about accelerations in units that are squared in the denominator. And yes, that is more traditional. And yes, ultimately, once you're used to it, it is probably better. But before I turn the page, I just want to make clear, don't get over freaked out or over excited about those seconds squared. This, like, we're going to convert this to miles per second squared. But like I've said before, that does not mean Michael J. Fox with a flux capacitor. That doesn't mean Back to the Future. We're not doing some crazy thing when we square seconds. We're not saying like time squared, enter with me, the square dimension of time. We're just saying miles per seconds again, and seconds times seconds. We're just shorthanding as squared. So miles per second squared is going to mean miles per second of velocity gained per every second. That's all it's going to mean. Okay, so we're going to do that unit conversion now on the next page. Okay, and here's the unit conversion, and the answer that I think we get if we stay in scientific notation. You'll get this answer at the bottom page, which is, I think, approximately 1.39 times 10 to the negative fourth miles per second squared. You also, some people, you could leave it as a fraction if you like. You might have gotten some people, right? I'm going backwards here on purpose, okay? Just first of all, you can check your answers or so you can feel like we're making progress. Like the ultimate answer I get if we convert to miles per second squared is approximately 1.39 times 10 to the negative fourth miles per second squared. That's a tiny, tiny number. If you want to leave it as a fraction, please, Quark bless America, be my guest. You can leave it as 1 over 7,200 miles per second squared, or miles per second. I'm going to show you how I do the math in what, because it's a unit conversion that's a little clunky. I'm going to show you, walk you through that once, and please stay with me, even though I know we all hate unit conversions. Well, we don't. I love them now, but I hated them for like 4 decades of my life. So I'm going to do it precisely because I think we all hate them, not because I think we all love them, and because I want you ultimately to love them. But before I even get to the unit conversion part, just note my final answer is a teeny tiny number, right? Like 1.39 times 10 to the negative fourth miles per second squared. Like, what's up with that? Yo, well, think about it. Like that actually should make sense. I'm not saying I could have predicted that it would exactly be that number, but if I were to start this problem by just making a rough prediction of what kind of number I would expect that I'll get a very tiny number. Like, and if I don't, I should check my work, because if every minute we're gaining a certain number of miles per hour, okay, and we get this, like 30 of them, right? Well, I mean, I don't think we're gaining as many miles per hour every second. Like, it takes me a full minute to gain 30 miles per hour. I think in a second, I have only done 1/60th of a minute. So I'm only going to gain like about 1/60th of whatever of that 60. And not only that, that's how many miles per hour of velocity I'm going to gain every second. But if I'm doing a certain rate of miles per hour, if this car, gets up to a speed of 60 miles per hour, it's certainly traveling way less than 60 miles in a freaking second, right? So in other words, I'm barely gaining any number of miles per second every second, since a second is such a tiny, tiny fraction of an hour. So I think it's not surprising that I'm going to get a really tiny number as my answer. But how did I get that number? Okay, unit conversion. So now I'm looking up here. So bear with me for a second. I'm sure, in fact, well, I might ask you a second. I'm curious. Feel free in the chat. I'm not going to stop and make you, but feel free in the chat, publicly or privately, just to let me know if you actually did get this question right, or if you got something else. I'm not judging you. Like, I'm actually just trying to figure out how fast or slow I should explain. You got awesome. I just see one person in the direct chat. That's great. And also that direct chat person, I hope you've gotten back some of your homeworks now. I still owe you a lot, direct chat person, but I think you got a couple of them a couple of minutes. Yeah. Okay, cool. Oh, and another direct chat person. Okay, cool. All right. So I won't overdwell. Cool. Oh, and another direct. Great. So you got it right. A lot of you in the direct chat. Now, that, of course, I know that if you got it wrong, you're less likely to be saying that in the chat. So awesome. Oh, okay, cool. Oh, that's very honest. Oh, I'm getting a lot of, well, I feel like we're having group therapy here in the direct, in a good way. Cool. No, seriously, the feedback is good. I mean, it's really good. And I always understand, of course, it's more likely that you'd put something if you feel confident than if not, but let's break that habit. And I love these, like, I got it wrong, but I understand now type of direct, it makes me, okay, cool. So let me say this. Yeah, I do think that is the right answer. And I would accept either form, 1 over 7,200 or 1.3. But let me say to all of you, okay, like unit conversions. I know you had them coming out of your ears in like chemistry and in high school. And I know most science classes sort of start with them, and it's like turns off. Half the reason that half the people in the world don't take science classes is because they get so turned off by the metric system and unit conversions. I get all that. And I hated all of it too for the longest time. I thought it was just like crap that I had to do to satisfy my teachers or my professors. Now, it turns out there's a reason that we do all that stuff early in class, because it turns out not just to be super important, but it actually turns out to be really helpful once you're comfortable with it. But people aren't comfortable with it until they're comfortable with it. So let me say I'm seeing more in the chat. Great. Awesome. I told you. And all the stuff that you're putting in the chat, remember, you could submit this all for participation, really. And remember, and if you're showing video, put that in the video slot. If you're showing an avatar, put it in the avatar slot. And those are different, but blah, blah. Oh, cool. I love it. And anytime any one of you says you didn't get it right, but now it makes sense. I don't know if if you understand that that's like the highest possible form of making my life feel valuable. I don't know if you're aligned with it, but like that's awesome. Because that means our time here is worth it. So let me say, at the risk of wasting any more of your time, if you did get about unit conversion, here's the deal. Oh, someone's here. Sorry. Hold on. Here's the deal. Here's my relationship with unit conversion. It is actually really important. Even when people get it, for a while, they still don't find it interesting or worthwhile. They still kind of hate it, even when they get it sort of tenuously. I want ultimately, like with everything else, with trig, with calculus, first I want you to get it, sure, but then I want you to get comfortable enough with it that you actually like it and are willing to play around. Like science, if you want to stay in science, we want to be able to enjoy it eventually, right? So, or enjoy it like we used to until our spirits got killed by all the work we have to do. So think about unit conversion. What at this stage, my experience is that with a lot of you at this stage, having taken Gen Chem and having gone through high school, like a lot of you are pretty good at unit conversions. I'm not saying you're not. But what often happens with unit conversions is people have their different methods, and they kind of always know that when you have to do a unit conversion, that you know the unit conversion factor, right? Like for example, here, if we're going to convert, if you look, we're being asked to convert a number that's in hours per, we're being asked to convert a number that's in miles per hour per minute. We're being asked to convert that to miles per second per second. I mean, that's a clunky unit conversion. Right, I'm making it look like it's just a couple of lines here because I'm trying to clarify it, but it's actually a lot of steps even in my mind, and it's certainly super annoying looking that we're going to convert a bunch of hours and minutes to seconds, and they're in the denominator. Like, that is yuck-o-rama. So I'm saying that where a lot of us often are with unit conversion is we would know in our minds, like we're going to have to use a conversion factor. And I know that there's 60 seconds in a minute. And I know that there's 60 minutes in an hour. And I'm going to know that I'm going to have to use that. But then what a lot of us do half consciously is we go, all right, I know like 60s are going to be involved. But the question is, am I going to multiply or divide? That's what I'm like never clear about. So I like refresh my, like, do I multiply or divide? And then when I think I remember whether I multiply or divide by 60 or 60 again, or 60 again, then I go, oh, but crap, this is all in the denominator. So whatever I think, do I have to flip it since it's in the denominator? And then it becomes this whole jamboree of, so here's my advice. The way I do unit conversions, I never, ever ask myself, am I going to multiply or divide? Because frankly, that's where I always get tripped up. I do. There's tricks for it, but what I do is I always multiply. I always multiply in the way I think of it. I'm never dividing. I'm always multiplying. And I'm always multiplying. So this is my one speech about unit conversion. Okay, we're going to do this once, bear with me. And we're doing it on purpose here because we got stuff going on in the denominator and it's squared. So it's kind of as clunky as a unit conversion could be. So look at my method. I write down A equals 30 miles per hour times minute, right? Then I'm going to multiply by what I call by a fraction. And the fraction, I'm always allowed to multiply by some kind of fraction. It might be a top-heavy fraction. It might not. We'll decide that in a minute. But I'm always going to multiply by some fraction. I'm always allowed to, as long as the fraction is just a fancy way of saying 1, right? Like as long as the fraction is like 7 over 7 or 14 over 14 or 23,000 over 23,000 or x over x, as long as the numerator and the denominator are equal to each other, and then the fraction all just equals 1. And so I'm allowed to multiply it because it doesn't change anything, right? Like this is the theory of unit conversions. You're always allowed to multiply by what I call the well-chosen 1. You're going to choose a 1, you're going to choose a fraction where the numerator and the denominator are equal to each other so that it's legal, right? And the numerator and the denominator are going to be like unit conversion factor, right? Like 60 seconds happens to be in the denominator here, equals 1 minute, which is in the numerator, right? The reason I can multiply by that whole thing is because 60 seconds is just one way of saying 1 minute. They're the same thing, right? So I'm going to multiply. So I'm going to try to get rid of the minutes and end up in seconds. That's my goal. So I'm going to put 1 minute in a fraction. I'm going to put 60 seconds in the fraction, and I'm going to multiply by that fraction. I'm definitely multiplying. I'm not going to divide. The only question is, am I putting 1 minute in the numerator or in the denominator, but I'm definitely going to multiply, and I'm definitely going to multiply by a fraction that has minutes and seconds, like, 1 minute and 60 seconds. Only question is, I'm going to put minute in the numerator and denominator, and the way I decide. So that's the only decision that has to be made. If you do this method, always multiply by a fraction. Your fraction is a well-chosen one. The only question is, is the fraction like top heavy or not? And the answer is, you arrange it so that the thing you want to get rid of cancels out, and the thing that you want to end up with doesn't cancel out. So I'm trying to get rid of minutes here, right? I'm trying to convert in my first step from minutes to seconds. So I put the minutes on the top of my fraction so that they cancel out with the minutes in the bottom of the original answer. If the minutes had been in the top of the original answer, I would have put my minutes of the conversion factor in the bottom. I'm just literally arranging it so that what I don't want is like a diagonal and crosses out. Again, there might be 70% of you might be going, yeah, I've always known that. Like, really? And 15% of you might be going, well, that was supposedly helpful, but I didn't follow a word of it. So and I'm sorry to both groups, but if there's 5% of you who are like, oh, okay, like, I guess I always knew that, but I never really thought about it that way. Like, it seems like that's what I'm always done, but I never quite thought of it that way. Maybe that will. All right. So from now on, I'm never going to worry about dividing or multiplying. I'm just going to multiply by a fraction, and I'm just going to arrange the fraction so that things convert. If 5% of you are thinking anything like that, then I've done my job. And I apologize to all the 95% others of you, whatever the percentage. So I put 1 minute over 60 seconds because they're equal to each other, and it's a well-chosen one, but I put the minutes on top so they cancel with the other minutes. Okay. So I do that. Now I have 30 over 60 miles over hours times seconds. Now I'm going to do the thing again. I want to get rid of those hours and change them into seconds. Now here, I'm skipping a step because I'm trying to move on and not bore everybody. Like I say in my mind, okay, I'm trying to get rid of hours and convert to seconds. I know there's 60 seconds in a minute and there's 60 minutes in an hour. So yes, I'm not dragging all of that out. I'm just saying if there's 60 seconds in a minute and there's 60 minutes in an hour, then there must be 60 times 60 seconds in an hour. And I do believe that 6 times 6 is 36. So I believe that 60 times 60 is 3,600. Like that, I'm saying, if you need to write that down, please do. But I literally say again, then 1 hour is the same as 3,600 seconds. I'm going to multiply by that fraction. My only decision that I have to make is whether to put the hours on top or the hours on the bottom. I'm putting them on the top so they cancel out with the hours in the bottom of the answer that's already there. So I write it. So I wrote 30 over 60 miles per hour seconds times 1 hour over 3,600 seconds. So the hours cancel. I'm left with miles per second, which is the same thing as miles per second squared. So I do the math, and so I have 1/2 times 1 over 3,600. That's 1 over 7,200, and you do that on a calculator, and you get essentially 1.39 or 1.4 times 10 to the -4. Okay, I apologize if I drag that out. If I if that was too much, we're never going to do that again. But that's my speech on unit conversion. It really doesn't have to be that bad, but it is that important. And the bottom line is we get an answer now that has 2 units of time in the denominator, always true for acceleration. From now on in my life, in the metric system, velocities are in all velocities, instantaneous, average, whatever, initial, final, all velocities are in meters per second. All accelerations from now on are in meters per second squared, meters per second. Okay, so that's that. I'm going to move on, but please stop me if I shouldn't, or please speed me up if that's what you prefer. All input welcome in the private chat. Okay. Oh, I know where I'm going now. Okay. So now what we're going to do, I'm looking, because we're going to finish the sheet by Cracky. We're going to finish homework 4 today, or my name isn't whatever my name is. But in order to do that, hold on, what we're going to do, I'm going to pause for a second. Like there's 3 more questions on the sheet. Hold on. And I hope you're looking at the sheet in front of you. Like I can't be showing the sheet and the answers. I mean, maybe I could, but I can't handle that. So if you're looking at the sheet of homework 4 in front of you, we just did problem 3, problem 3, Roman numeral 3. There's problem 4, problem 5, and problem 6 left. 6 is what I really want to talk about and end the class with, and it will generate a new equation for us, like the very last one. In order to get to the last one in time, and this should work because it worked this morning, I would like to talk through somewhat, maybe quickly, problem 4 and 5. I'm not going to write these down. I'm just going to talk them through and you'll take notes. But I'm worried if I start writing them down, I'm going to get myself bogged down and never get to question 6. So I'm going to wait, I'm going to change the view for a second on the screen. I would just like your confirmation affirmation. If it's clear, if it's okay and clear, if it's clear to you and okay, then I'm just now going to talk through the answers of problem 4 and 5 of this sheet. And again, by the way, sidebar, even if you haven't done this yet, you still can do it. Even with me talking through, you still have to, to submit a proper homework that gets all the points, you still have to walk through all the steps and blah, blah, blah. And I'm not about to walk through all of them. So it's not cheating. If you did the homework in advance, like I asked you to, I think you're getting more out of class. I think you're getting more out of all this, and I think you'll be in a better position for the exam. But if you didn't do the homework in advance of class, it is not cheating to use class to help you do the homework. So I'll still accept it, just to make that clear again. But so I would all the more encourage you to take notes on this part. But can I get an electronic show of hands if it's clear and okay with you that I'm now just going to talk through? Thank you, Abdel. I'm just going to talk through and keep them up for a second. So just get it. I'm about to just talk through problems 4 and 5. I'm not going to write it down. You're going to write it down. Okay. Thank you, Abdel. Thank you, Gianna. Thank you, Alejandro. Thank you, Sarah. Thank you, Kay. Thank you, Ashley. Thank you, Stephen. Thank you, Jose. Thank you, Tobias. Thank you, Katya. And you guys, the rest of you are okay. I mean, like, cool. Thank you. All right, I'm just going to say it again. I'm not trying to single anybody out. Maybe someone's getting a cup of coffee right now, but just to say, we're about to talk through the next 2 problems, 4 and 5 from homework 4, whether you've done them or not. Okay, cool. Thank you, Jocelyn. Totally appreciate it. Oh, thank you, Brian. I'm sorry. I mean, thank you, people who might be in the direct chat or not. Okay, thank you, folks. All right, I'll take that as consensus. All right, you can put your hands down. So I'm going to change the view on the screen again. We're going to go to problem 5. But again, now I'm going to, even if I start talking fast like I do, that doesn't mean you're not supposed to stop me. It means I'm talking fast as long as you don't stop me, okay? So we're going to go. So there's not going to be anything written for a second. You're fine with it? Okay, cool. Okay. Oh, sorry. And thank you for direct. I see there's some things in the direct chat I didn't respond to. Got you. Thank you. No problem. All good. Thank you. And thank you. Okay. So now, in fact, just to really be clear, so I'm going now to problem 4 and 5. I'm going to switch the screen sharing so you can see the questions this time instead of the answers. So I think. Yeah. Okay. Yeah. So you're all right. Cool. So we're talking about. Yeah, I think you can see the screen. All right. So we're talking about acceleration. Okay. Problem 4. And I'm watching the clock too. I'm just going to talk about acceleration in direction 1. Okay. Again, this is just practice. Kind of practice with the equation, straightforward equation, but it's also to drum in. This is not all crazy about units anymore. This is to drum in how negative signs and positive signs work. Okay, that's the purpose of this question. So it gives you these facts: the Audi, the Buick, the Camry, the dirt bike. You can see them on your screen. Question A says, choose which direction, east or west, will be positive and which will be negative. It's up to you. Now, it is up to you. That's no joke. It is up to you. But now if you're handing in this homework, what that means is I'm very specifically looking for a diagram here. Like the diagram is the whole deal here. It could be a very simple diagram with just like an arrow and a plus sign and a minus sign, okay? But we need a diagram here. Here's what I'm really saying is it's not a joke that it's up to you whether east or an arrow, whatever. It's up to you whether east is positive or negative. You could choose either one. If you choose east, you're going to get a bunch of answers that are going to be exactly the same as my answers. Because I'll tell you right now, I choose east to be positive for this problem. I draw a little diagram in my head where I make east positive, I make west negative. That's my choice. If you happen to make that same choice, every one of your answers is going to match up with mine. If you make the opposite choice, your answers will be different from mine. Like minus signs won't match up with mine. But your answers will still be right. I mean, if they're self-consistent. This is an example of Galileo here. Like I'm choosing one coordinate system. I'm choosing one inertial reference frame, but you might choose another. And the laws of physics are the same in all inertial reference frames, in all coordinate systems. We can do physics in any, we can pick any coordinate system we want, any perspective we want, as long as it's a perspective that is not speeding up or slowing down, as long as it's inertial. Whatever answers I get in my reference frame are just as correct as whatever answers you get in your reference frame. And they really might be different, and they'll both be correct, but they're both specific to our reference frame. In other words, answers don't mean anything unless you know the reference frame that they're measured in. So on the one hand, the freedom here is we can choose any reference frame we want. We can make east positive or negative. That is not a joke. But whatever we choose will affect our answers. So therefore, we need to make a choice. The one thing we cannot do is choose not to choose. We cannot just skip the, really, it gets more and more important as you progress in physics. We have to make an assignment of what direction means what, so that all of our information makes sense. Okay, so this is practice in the Galileo idea, and it's also practice in seeing how the negative signs are going to mean direction. Direction matters in physics. So I'm choosing to say east is positive, west is negative. You could choose whichever you want, but if you didn't choose one, you wouldn't get the points. And now, given that choice, I'm going to question B now. My initial, I asked me to write down the initial and final velocity of each vehicle using a positive and negative sign. Okay. And notice initial and final are two versions of instantaneous velocity. Like initial velocity is an example of instantaneous velocity. Final velocity is an example of instantaneous velocity. They are each velocities at particular instance. Okay, so I say, according to if I'm considering east to be positive, then my Audi, the initial velocity of my Audi is positive 10. The final meters per second. The final instantaneous velocity of my Audi is positive 50 meters per second. The initial velocity of my Buick is negative 10. The final velocity of my Buick is negative 50. And I'm going to keep going. This is all like everything in physics. If it makes sense to you, then it makes such sense that you're like, duh. But it's very possible that some of this does not make sense to people, and they should not be ashamed. These negative signs may start being confusing to some people. Tell me in the chat. Do not be ashamed of yourself. I hate shame. So the Buick is like, it's all true, but none of it's obvious until after. It's only obvious once you know it. So the Buick, its initial velocity is negative 10. Its final velocity is negative 50. The Camry, its initial velocity is positive 50. Its final velocity is positive 10. The dirt bike, its initial velocity is negative 50. Its final velocity is negative 10. Okay, so that's all the answers to B. Now, the answers to C. And I'll tell you right now that some people in the other class, maybe everybody's going to rock this, and great. I'm not telling you, it's not a trick, but some people in the other section did have questions about this, and nobody got shot for asking those questions. In fact, I got points for them. So here we go with C, and and positive and negative signs totally matter here. It is all about. So if you get something different from me on a negative side, don't just say, oh, I got the same, whatever, I just differ on the minus side. Like the minus signs like are the issue here. So what I get for my answers for C, is the Buick, the Audi, the average acceleration is positive 4 meters per second squared. Positive 4 meters per second squared. In other words, positive 40 divided by 10 is positive 4 meters per second squared. That's the Audi. The Buick is negative 4 meters per second squared. The Camry is negative 4 meters per second squared. And the dirt bike is negative 4. No, I'm totally kidding. Sorry. The dirt bike is positive 4 meters per second squared. So the Audi and the dirt bike had positive 4 meters per second squared. The Buick and the Camry had negative 4. If you designated that east is positive, then those have to be your answers. I mean, for it to be right. if you agree with me that positive is east, then those are the four answers. If you said that positive, excuse me, if you said that east is negative, that's totally fine. Then literally your four answers would be literally the reverse. Like, but all of them would be reversed. So it's like two options. Like you either got exactly my answers or you got literally the reverse of my answers. But if you didn't designate that positive is east, or if you got like a scatter shot of answers, then you really do want to pause and either ask yourself or ask me in the direct chat what's going on. Because we're starting to get strict and precise in science now in this class. So, but those are my answers. But it looks like so does anybody want to, can anybody just tell me in the direct chat? If you did get it right, just tell me in the direct, just give me some feedback in the direct chat if you're okay. If you're okay, just tell me you're okay. That's fine. But I would like to, or you're smiling. That's cool too. Oh, chat. Okay, I'm looking at. Oh, cool. Awesome. Thank you, direct chat person whose homework I owe her or him many there unto. Stephen, thank you for going public. You're okay. Cool. All right, awesome. Is there anybody that wants to admit? Oh, cool. Direct chat person. Thank you. Awesome. Thank you. Oh, no, it's fine though. No, guys, I want you. I'm not telling you that you have to be private. I'm just giving you permission because I know it's, but the more public we can be by the end of the semester, I think the better for all of us. I'm just giving you permission to be nervous, but I don't want you to be nervous ultimately. I'll probably make people, but okay. So also, if anybody wants to put in the direct chat, like I did get it wrong, but I get it now, which people were saying before, that helps me too. At least it makes me feel like I'm not wasting your time. But okay. But all right, in any case, but we're good. Oh. Okay, I'm totally not going to read this person's name, but this is exactly an example where I can see why this person would want to go private with this, but I wish ultimately people would feel comfortable. So someone has privately said, and I'm not going to say his, her, or theirs name or anything, but someone said, LOL. So I also know, I think they're okay with me. Someone said, I never get the questions right, but I always understand the questions after you do them. Listen, I'm really glad at least one person's admitting that. And like maybe never is probably even strong, is probably even not giving that person's self as much credit as they deserve. But like, can I just say again, sidebar, I've been doing this for 30 years, people. And that is generally at some point, that's the way everybody feels at some point in physics. And you might not feel that way yet, or you might, at some point, people get to the point where they're like, I don't know what the heck is going on about but it always makes sense in class. So I always think I'll be okay. And then I'm not. And then I think I'm okay. And then I'm not. I get it. We're trying to eventually elevate, but there's nothing that's good. I mean, that's why you're getting your money's worth now. But eventually you will be able to do this without me. But okay. Oh, okay. Okay. Very honest. See, I'm getting more on. It's all about group therapy here. I'm getting, all right. So someone's very politely egging me on to the next question, which I appreciate. So I'm going to say the next question is actually just trying to make sure we get a takeaway from this last question. So let me say this, and I am moving on, I will move on. But with question 4, what it's really trying to drum into everybody is surprise. It's saying, okay, from now on in physics, we always use the word acceleration. We'll never use the word deceleration in physics. We will always say acceleration, but sometimes acceleration can be positive and sometimes it can be negative. But what we are saying, what we're trying to get across right now is, and this may be a surprise, is that positive acceleration does not always mean speeding up. And negative acceleration does not always mean slowing down. What we're trying to get across with this case of the Audi, Buick, Camry, dirt bike thing, we're trying to say there's really 4 cases. And really, positive acceleration can mean one of 2 things. It can mean moving in a positive direction, speeding up, or it could mean moving in a negative direction, slowing down. And conversely, with negative acceleration, what we're really trying to say here is, remember, positive and negatives are just 2 different directions on a number line or on a coordinate axis. And from here on in, well, okay, all right. So I guess I'll literally go to question 5 now, because someone is politely asking me about that, and I appreciate it. So question 5, acceleration and direction, like 2, part A says a particle is moving at, I wonder if I can, wait, can I zoom in on this? Sorry. Let me just see if I can actually zoom. I know I can. Hold on. Sorry. Oh, that's nice. Okay. Okay, so that's a little bit better, right? I think, Grandma. I'll do it one more time. Did I just call? I call myself Grandma. It's not you. Okay. Okay. So look, so Roman numeral 5, a particle is moving at velocity negative 17 meters per second. What is its speed? So this is just a refresher or reminder that if your velocity is negative 17, your speed is 17. Speed is the magnitude of the velocity vector. Speed is just the amount. So if someone says I have a velocity of negative 17, what they're saying is I'm going 17 meters per second, but I'm going in what we're calling a negative direction, i.e. I'm either going south or I'm going west or going backwards. Like someone has to know the coordinate system to know what I mean by negative, but definitely what it means is the opposite direction from whatever anybody called positive. Like that negative sign is real information. It's not weird information. It's not saying that I'm slowing down or anything. It's just saying that class ends in 19 minutes and then I'll be off. Okay.
But we're going in like 30 minutes.
Wait, okay.
So get off right now.
Class ends in 19 minutes. You can quickly say hi if you want, but I have to. Okay, so when class ends? So what was it?
You're saying words like stupid idiot. You're talking about stupid idiots.
Possibly true.
Like you are.
See, that's a little aggressive. It's a little aggressive. A little unnecessary, but I understand his feelings. It's this whole thing of working at home in front of children. Anyway, I love him like a son, not coincidentally. And by the way, if you're thinking, oh my God, you just let him get away with that, you're such a pushover, what a loser. Well, yes, but also don't forget, Galileo, the sun is the center of the universe. Okay, just kidding. So if the velocity of an object, and I will look in the chat in a second, although I have a feeling at least one thing in the chat is something about my parenting skills. If the velocity is negative 17, then that means the speed is 17, and it just means the object is moving in a negative direction, which is ultimately a real direction, just designated with a negative sign to mean opposite of the other direction, opposite of positive. So why that's important? Well, okay, so that's answered question B too. The negative sign in the velocity indicates a particular direction. What determines which is negative or positive is the predetermination you make about your coordinate system before you even start putting information in or making measurements. You designate your coordinate system, you choose your frame of reference, you say, am I looking at the universe from the inside of the train or from the platform, from the earth or from the sun, right? This is all about Galileo in the end. What am I comparing things to? Where's my coordinate grid? Once you designate that, then you start getting numbers. Numbers indicate direction in that coordinate system. And so if we now have an equation or a definition that says acceleration is change in velocity per time, and if velocity numbers take into account direction, which they do, and if velocity numbers can be positive or negative, we now have to start thinking about negative positive in an intricate way. What we're now saying to get to part C here is, well, the answer to part C, to answer direct chat person, is in some experiments, some hydrogen atom is found to have a positive acceleration for some segment of its motion. Is the hydrogen atom necessarily speeding up? Answer, no, it's not. Like if you look up, just because something has positive acceleration does not mean it's speeding up. If you look at the Audi Buick Camry dirt bike example, that's what that's trying to show. If I say that something has positive acceleration, what that means, literally, mathematically, and always, is it means it's gaining velocity. That does not necessarily mean it's gaining speed. It means it's gaining velocity. It means that the velocity numbers are getting higher. So that could mean, so that means if the velocity numbers happen to be positive, it means they're getting more positive. I.e., if the thing is moving in a forward direction, then if it has positive direction, then if we say it has positive acceleration, that means, okay, those positive numbers are getting bigger and bigger. They're getting increasingly positive. Okay, the thing is speeding up. But if an object, if this hydrogen atom happens to be moving south or west, or whatever we happen to have designated as negative, if the hydrogen atom happens to be moving negatively, and if it had a positive acceleration means its velocity numbers are getting bigger and bigger. They're getting more positive. If its numbers happen to be negative, say it had a negative 20, a negative 17 velocity. And then a minute later, it has negative 9 velocity. Really think this through. That means its velocity just got bigger, because negative 9 is a bigger number than negative 17, right? Negative 9 is a bigger velocity than negative 17. So if something went from negative 17 to negative 9, that means if you do the subtraction and whatnot, its velocity went up, but it didn't speed up. It got slower, right? Because its speeds were going from 17, absolute value 17, to a speed of 9. So if something went from negative 17 to negative 9, that would be an example of a positive acceleration, but a positive acceleration of the dirt bike kind. It would be a positive acceleration where that represented something moving in a negative direction, slowing down. So my answer to C of question 5 is no. Positive acceleration either means speeding up while traveling positively, or slowing down while traveling negatively. Just like negative acceleration either means slowing down while moving positively, or speeding up while moving negatively. And all of this is meant not to contradict your English idea of the word acceleration. All of this is meant to start with your idea of acceleration. Don't throw it away. Whatever English idea or whatever your native language is, whatever idea you have of the word acceleration, start with that. Don't throw it away. This is all based on it. But then what we're doing here is we're making it more precise, more specific, more detailed, and more ultimately mathematically consistent to cover more cases. So you want to incorporate all this into your notion of acceleration. Acceleration means change in velocity per time. It doesn't mean change in speed. It means change in velocity. And velocity takes into account direction. So acceleration takes into account direction. That's what I'm saying on that. We still have 13 minutes to go to the final problem, which will be fine. We need to do that, but I'm going to just quickly check the chat. I have a feeling the chat thing might, but I also, in the chat, I'm going to check, but the person who asked me directly to go to that question, I would like to know from that person whether I did address what he, she, or they were saying. Okay. Oh, he, or they did. Thank you. That's awesome. Okay, that's great. I really appreciate. And please put that in for participation for full circle and all that. Okay. Wait, I'm looking back in the chat now. D. Okay, D. Oh. Okay. Oh, okay, but 4. Okay, sorry. I get you now. Oh, thank you, Kay. Okay, so hopefully the direct. Okay, cool. Thank you, direct chat person, and thank you, Kay, for the public shout out. And yeah, until he was like totally rude, and I totally. Oh, wait, what just happened to the share? Just wait, did I just lose the share? Okay, all right, now. Wait. Oh, great. Great, direct chat person. Thank you for all the feedback, Director. Boy, you deserve more feedback on your homework, really, for all this feedback you're giving me in class. And I'm not really joking. Okay. It's noted. It's very noted. Okay, so now I want to go to the last question, which we have 11 minutes for. Now, the last question is a little bit more deep. The last question, by which I mean this one in the middle, 6, right? Now, first of all, I mentioned this in Google Classroom a long time ago in the stream. Part C, just cross it out. I apologize. Part C is just garbage. It's like from an old, when we used to have a website, which I really should put back up, but I haven't had in a while so just forget C. It's all about A and B, and I apologize, in question 6. And the goal of this 11 minutes is we're going to generate a final equation from this information in 6. So in question 6, part A, you're given these lists of numbers and you're asked to get the average of each list, right? I'm about to switch the screen shares, but what do I do for each of those lists? I do what I would do in a math class. I add up all the numbers and I divide by the number of numbers to get an average. Like I'm doing arithmetic mean, so to speak, a mean average I'm getting. In fact, I probably should have specified that I'm talking about mean here. So like in the first one, I add 1 + 2 + 3 + 4 + 5 + 6 + 7. I add them all up. I get 28. I divide by 7 because there's 7 numbers, and I get that the average is 4. Okay, same thing with the next one. I add up 4, 5, 6, 7, 8, 9, 10. I add them all up and I get 9, 15, 22, 30, 39, 49. I divide by 7 because there's 7 numbers and I get 7. So I'm going to switch screens now. I'm going to switch screens now. Wait, what? Oh, yeah, okay. So I'm switching screens. Boom, boom. Okay. All right. And here, hello. Okay. So I get the averages. I just add them all up, divide by 7. You know, sometimes it takes longer. And again, if you're doing your homework or when you did, you show all your work, you even put in a diagram, even though these are just freaking numbers. But now I'm being a teacher. I'm racing ahead a little bit. I'm just giving you the answers. So those are the answers: 4, 7, 9, 27, 11, and 20. Okay, fine. But then it starts asking this sort of probing question about like, what's going on here? Is there something different about any of the rows from the others? And yes, to cut to the chase. Well, to cut to the chase, in the first 5 examples, you can add up all the numbers and divide by 7, or then you could start noticing as you're doing that, that because all these numbers have been arranged in order conveniently, the number you get as the average each time ends up just being the middle number of the whole set, right? Even in example 5, where there is no number 11, there's like a number 10 and there's a number 12, but there's no 11. Still, if you just arrange all those numbers and look for what's dead center in the middle, in other words, in fact, should I go back? Yeah, in fact, I'm going to go. Yeah, I'm even going to go back. Can I do this? Let's see, with 9 minutes left. Wait, I'm going to go back to the other thing. Yeah, sorry. Right. If you look at that last set of numbers, I'm sorry, the second to last, number 5, like, whoa. Hold on one second. Wait, something's wrong here. Oh, right. Okay. Yeah, even though, I tricked myself. Okay, even that second to last one, they're like me years ago was being tricky and didn't even provide the numbers in order because I don't have to, right? The numbers are just the numbers. But if you arrange them in order, if you look at number 4, you may or may not have noticed that the 6 and the 8 are like, they're written in a different order, which is fine. Like no one says I couldn't do that. But if you put them in order, if you just rearrange them so they're in ascending order, like all the other ones before it. So if I'm talking about row number 5, and I know we have 8 minutes left. If you're looking at row number 5 and just rewrite it as 6, 8, 10, 12, 14, 16. If you do that, you will, and you add them all up and you get the average. The average is 11. You'll notice that 11 is the number that would come smack dab in the middle of those. Like there's only, in other words, there's an even number of numbers there. There isn't an odd number like the other ones. So there is no number that actually is in the middle. But if there were, it would be 11, right? In other words, I'm going a step further here now, because I know you just saw the equation on that page. But so I'm saying, first of all, with those first 5, you could get the average, the mean, by skipping steps, by not even adding up all the numbers, by just actually selecting out the median. For those first 5 choices, the mean is actually turns out to be the same as the median. You could just pick out the middle number and you'd be right for the first 5 rows. If not for the last one, but for the first 5, I'll go a step further. Not only could you just pick out the middle number, if you want to know what the middle number is, even if it's like missing as it is for the 5th row, if you think about this, you may or may not notice, you could literally, instead of averaging all the numbers, adding them all, you could take the first, like look at the first row. You could literally take the lowest number 1, add it to the highest number 7, add them together, get 8, divide by 2, because 2 numbers you just add together, and you get 4. Like I'm saying now, something you might not, maybe you noticed, maybe you didn't. That with those, and that would even work with the 5th row. If you take the lowest number 6 and add it to the highest number 16, you get 22. Divide by 2, because you just added 2 numbers together, and you'll get 11, which is the middle of that. In other words, with those 5 rows, if you want the average of all the numbers, and this would have worked even if there was 17,000, numbers in the list. If you want the average of all the numbers, instead of adding them all up and divided by all of them, you could literally just select the middle one. And even if the middle one wasn't obvious, you could just literally take the lowest and the highest and average them together. And that would give you the middle one, and you'd be done for the first 5 rows. But it only works for the first 5. It doesn't work for the 6th, even though the 6th is arranged in order. And even though the 6th is a pattern, it's definitely a pattern. It's a very important pattern, but it's not the same pattern as all the others. Right. And in the middle one, you get that the average is, I think, 20 or something, which is not the middle number, like by any definition. What's going on here with 5 minutes left? What's going on here is all of the number rows, besides the very last one, have numbers that are changing, but by an unchanging amount, right? They're all stepping up by a constant interval or stepping down by a constant interval. Whenever numbers change by an unchanging amount, like they're changing, right? 1, 2, 3, 4, 5, the numbers are changing, but they're changing by a constant amount. They each keep going up by 1, or in the second or in the third row, they're changing 3, 5, 7, 9, 11, but they're changing always by 2. So they're changing, but by an unchanging amount. There is a change, but there's no change in the change. Unlike the last row, there's a change and there's a change in the change. If you are somewhat comfortable about calculus, you might notice that what I'm saying is in all of the first rows, besides the very last one, there's a derivative, but there's no second derivative. There's a change, but the change is constant. There's a derivative, but the derivative of the derivative is 0. That's what I'm saying in calculus language. With that very last row, there's a derivative and a second derivative. Like the separation between the first 2 numbers, 1 and 4, is 3. Then the next 2 is 5. Like, 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7. So there's a change in the change. There's no third change, but what I'm saying is, to go back to the screen share, because I know we have 3 minutes. What I'm saying is, with 3 minutes left, this pattern of numbers that you're seeing here doesn't just only apply to raw numbers. Imagine that each one of those numbers was a velocity. Imagine that each one of those numbers was a new instantaneous velocity at a new second of time, or a new constant unit of time, right? So like our velocities were going 1 meter per second, 2 meters per second, 3 meters per second, 5 meters per second, 7, whatever. Those are all examples of acceleration. They're all changes in velocity, right? But whenever the change in velocity was constant, whenever there was acceleration, but no change in acceleration, so what I'm writing here, the new equation, and we've got 2 minutes, but here it is written on the right side of this sheet. I'm saying if and only if A equals A naught, if there is an acceleration that's always the same, if we're always gaining by 2 meters per second or always losing by 2 meters per second or something every second, then in English, the mean velocity will be the median velocity. Then and only then, if acceleration is constant, then we can get average velocity, double equal sign, by just averaging the first and the last velocity, adding the 2 endpoint velocities together and dividing by 2 to get the middle velocity. What I'm saying here with 1 minute left, and this is very subtle, I'm saying I tried to drill into all of us with the Grandma Grimm problem, the Little Red Riding Hood problem, that average velocity is not defined to be the average of velocities. Average velocity, triple equal sign, is displacement over time. But when and only when the velocity is changing in a constant way, then we can get a trick. We can use a trick to get average velocity. Then and only then, not in Grandma Grimm, not in the Hilfiger problem, but when acceleration is a constant, then we can get our whole average velocity by simply averaging the lowest and the highest together, adding them together, dividing by 2, and that will give us the middle velocity. The middle velocity is the average velocity when and only when acceleration is constant. So that's our final equation, v naught plus v over 2 equals average v, double equal sign. And that equation is our first double equal sign. It's not always true. It's not a definition. It's only true. It's about velocity, but it's only true when velocity is changing in a constant way. So it's our first of what are known as constant acceleration equations. It's not an equation about acceleration. It's an equation that assumes a condition known as constant acceleration. That's our first constant acceleration equation. It's our 6th equation of the class so far. Class is over. Thank you for being so patient. Such a wonderful class. We're done. I'm going to hang out if there's any questions. Yeah. Yes. Yes, Sarah. Awesome. Yes, yes, yes. It only counts as long as they're increasing or decreasing by the same interval. It's exactly what I'm saying. Sorry, I missed that 5 minutes ago, but yes, Sarah, awesome. I think she gets it. I think maybe hopefully everybody therefore gets it. I'll hang out if there's any questions. I'm not running, but you can run. But goodbye. Thank you so much. You are awesome. Oh, thank you. Thank you. Awesome. Awesome. Okay. Thank you. Changing it. Thank you. Thank you, guys. Seriously. Have a good day. Yes, I will. You too. I hope you enjoy the rest of your day. Awesome. Awesome. Have a great day. Oh, 2 days. Oh, yeah. And I have, yes, I will see you guys. Oh, my God. Right. Thank you for reminding me. Yes. See you next week. Oh, my Lord. Oh, thank you, Kit. Right. Okay. And you, okay. Oh. Cool. Thank you, everybody. Okay. This has been physics class. Goodbye.